So what we have to do to calculate the efficiency, right? The efficiency is going to be the net work, right? So the net meaning the total sum of the work, right? So by the way, there's going to be positive work here, but this is also going to be negative work, right? Okay. So it's going to be the difference between the positive work and the negative work, right? Divided by the heat that flows in. Okay, now notice that the denominator is not the net heat that flows in. It's just the heat that flows in, right? Okay, so we're going to ignore the heat that flows out. We're going to look at only the heat that flows in. Okay, so let's do this process by process. AB, BC, CA. All right, we can do this. I don't know why that's the sound that this makes. It just seems to be the right sound. I'm just feeling it in the moment here. Look how straight a line I can write. Okay, so this is a Q. This is our delta U. This is our work. There we go. All right, remember that these guys are equal, right? This plus. All right, equals this plus this. Okay. So for AB, the work was 3,600, and the change in internal energy was 5,400, right? Let's just double check that. 12 times, whoops, I'm typing 15, 12 times 3, right? Yeah, 3,600, 5,400. Right, and then the sum was 9,000 joules flows in, right? So this is heat flow in. This is change in internal energy, so it gets hotter. It actually stores more energy than the work it does, right? Okay, so for BC, our work is 0, right? We figured out that the change in internal energy was minus 5,400. And then we figured out that 5,400 joules of heat flow out, right? So that's the heat that flows out, right? Okay, and then for CA, we figure out that the work done on the gas is negative 1664, right? Okay, the change in internal energy is 0, and this is negative 1664. Okay, now, notice that for an entire cycle, the change in internal energy has to be 0. Why? Because we started here. We go around the thing, we end up there. Well, a spot on this graph dictates a particular temperature. The internal energy is just 3/2 nRT. If you're at the same temperature, you're at the same internal energy. So if you go around a complete cycle, the change in internal energy must add to 0, or you've messed something up, right? Okay. Now we can look at the net work done. Okay, the net work, not the network, but the net work is 3,600 minus 1664 is 1936. Okay, joules of network, right? If we look at the heat flow in, right, the heat flow in is 9,000 joules, right? So our efficiency is going to be 1936 divided by the 9,000 that flows in. Now, by the way, if we add this whole column up, right, we're going to get the network, right? Let's just try it. 9,000 minus 5,400 minus 1664. And sure enough, we get the network, right? And of course, that must be true. It must be that for a full cycle, the engine must consume heat and put out that same amount of work, right? Otherwise, energy would not be conserved, right? So for the full cycle, for A, B, C, A, abaka, okay, this is 1936 flow in. There's no net change in internal energy, and the net amount of work is this, right? Okay, now keep in mind that we've, of course, wasted a bunch of stuff. So 1936 divided by 9,000 is 0.21511111111. All right.